It's my great pleasure at this point to introduce Joe Halpern. So Joe received his bachelor's in mathematics from Toronto in 1975 and a PhD in maths from Harvard in 1981. And in between, he spent 2 years as the head of the maths department at Bawku. I'm sorry if I'm mispronouncing that.
No, that's right.
Okay, secondary school in Ghana. And then after a year as a visiting scientist at MIT, he joined the IBM Almaden Research Center
Um,
in 1982, thanks, where he remained until 1996 and also serving as a consulting professor at Stanford. In 1996, he joined the computer science department at Cornell, where he is currently the Joseph C. Ford Professor and was department chair 2010 to 14. So Halpern's major research interests are in reasoning about knowledge and uncertainty, security, distributed computation, decision theory, and game theory. And together with his former student, Yoram Moses, he pioneered the approach of applying reasoning about knowledge to analyzing distributed protocols and multi-agent reasoning. He's co-authored 5 patents, 3 books, and over 360 technical publications. And it's a kind of special privilege for me in some sense because I think the first AI research that I ever did, the first AI papers that I ever read were Joe's. Even now, I still kind of routinely have to make sure before I start on a project that Joe hasn't already written a paper solving the problem sometime in the early 90s before I was born. And yeah, I think this really just does speak to his kind of influence, kind of pervasive among such a vast range of topics. So extremely excited to have him here. And Joe, I will hand it over to you. Thank you very
yeah.
much.
So I'm coming to you from sunny room 309 in Chaminade. Unfortunately, my wife developed COVID 6 days ago. I'm symptom-free and have been, but unfortunately tested positive for the last 5 days. So we are concerned about safety. So I'm coming to you on Zoom, but I feel fine, just in case anybody's wondering. This is not going to be your typical talk. No AI, no machine learning, no reinforcement learning. This is sort of theory, distributed computing meets game theory. The ground rules are please don't wait till the end to ask questions. If you're confused, wave your hand. I'm sure they can handle it and ask along the way. So let me give you some background. So let me talk first about distributed computing. There are two views of the world. The distributed computing view traditionally, and which was taken over by cryptography also, has assumed that agents are either good or bad. Good agents do what they're supposed to do. They follow the protocol, think protocols like policy. Bad agents do all they can to subvert it. And the intuition was, these were people worried about space shuttles and so on. And they were worried that the system designer might write a protocol, but some computers might be flaky. They wanted guarantees that the shuttle was going to fly like it was supposed to. So they wanted fault tolerance. And their model of fault tolerance was there were some bad guys and some good guys. And so that's distributed computing. Game theory, by way of contrast, assumes that all agents are rational and they try to maximize their utility. So they wouldn't try to subvert a protocol unless it was in their best interest to do so. Now, both views make perfect sense. The goal of this talk is to combine them. It'll be a bit of a history and sociology lesson, some technical results, and then I'll argue why it's relevant to cooperative AI as well. So there are various threads. So let me start giving you, like one slide's worth of relevant background in distributed computing. So if you take any distributed computing course, a major theme will be fault tolerance, and a paradigmatic problem is what's called Byzantine agreement. And the story is that this story is due to Leslie Lamport. Leslie Lamport, by the way, is the LA and LaTeX. So their end soldiers up to T might be faulty. N and T are common knowledge, so everybody knows what they are, and everybody knows that everybody knows, and so on. And each soldier starts with an initial preference, which let's take it to be either 0 or 1. And in line with the story, let's make 1 attack and 0 retreat. So we want an algorithm that, as long as the non-faulty guys follow it, guarantees that all non-faulty guys do the same thing at the same time. So they either all attack or they all retreat. The point is you can't say anything about the faulty guys. You have no control over them. And to make it non-trivial, if all of the soldiers are non-faulty, and they all have the same initial preference, so they all want to attack, that's what they have to do. Without that second clause, I would have a really trivial algorithm, which is attack no matter what. That would guarantee that all the non-faulty guys do the same thing. So there are tons of results on this. There's a whole cottage industry on Byzantine agreement that goes back decades. So if soldiers can lie and cheat, you can reach agreement, provided that n, remember n is the total number of soldiers, is greater than 3t. Remember, t is a bound on the number of potentially faulty soldiers. And we'll get some insight into where this 3 is coming from later in the talk. With crash failures, now crash failures, if an agent is going to fail, they have the good sense to shut up and die. On the other hand, they could fail in the middle of sending a message. So, if in this round I'm supposed to send a message to 5 people, I could crash after having just sent it to 3 of them. That's allowed. But once I crash, that's it, I'm gone, I'm not sending any further messages. So with crash failures, you can always reach agreement as long as n is greater than t. If you have cryptographic techniques, in particular, if you can sign messages with unforgeable signatures, you can always reach agreement, again, as long as n is greater than t. If you can reach agreement at all, you can reach it in t+1 rounds, and that's a lower bound. And in fact, you need t+1 rounds, even if there are no failures at all, even if all the agents start with the same initial preference, and even if there's only crash failures. Still need t+1 rounds. That's provable. So again, this is just a flavor of the kind of results that people prove. There are lots. You can think of Byzantine agreement as a game between 2 teams of unknown composition because you don't know who the faulty guys are. They're one team, but whoever they are. So that was thread 1, the distributed computing thread. Thread 2 is the cryptography thread. So there's this paradigmatic problem in cryptography called multi-party computation. The initial paper was due to Andy Yao. Andy, by the way, won a Turing Award. There's another one by Goldreich, Macaulay, and Vigdis in '87. And Sylvia Macaulay and Avi Vigdis also both won Turing Awards. My point in stressing this is these are not obscure papers. You'll see why I want to make that point in a slide or two. We're talking about people who won Turing Awards. People are noticing these papers. And the story of multi-party computation is each agent has a secret input. Again, think of it as either 0 or 1, but not necessarily. Here the input could be much more general. You want to compute some function of that input without revealing any information beyond the output. So, for example, each of us has a salary, and we want to know what the highest salary is. So that's a function of the inputs. At the end of the computation, we want to know the highest salary. And we don't want to know anything beyond that, beyond what we can figure out knowing that. So we know that somebody has to have that salary, but we don't know who, for example. The intuition is, and this intuition was made precise back in the 80s in these papers. Imagine you had a trusted mediator. Think of a mediator as a third party. And each of you sends the mediator your private information, and the mediator broadcasts the answer. And there are protocols for multi-party computation. And again, the picture that they had was there were good guys and bad guys. And just like the distributed computing literature, and you could do it as long as n, the total number of players, was greater than 2t or greater than 3t, depending on the underlying assumptions, how bad guys could be. Okay, that was thread 2. Let me talk about thread 3, which is mediators, which will bring us closer to game theory. So consider an auction where people do not want to bid publicly. Why? Because public bidding reveals useful information. So when you have bidding, for example, for oil drilling rights offshore, off the shore of Brazil, you could bid for them publicly, but if one company like Exxon bids high, that's revealing to the other companies that their geologists think that that tract is valuable, and they might not want to reveal the work that their geologists have done. Again, if we had a trusted third party, we'd be all set. Each company sends their bid privately to the trusted third party, and the trusted third party announces who won. So if we had a mediator, we could easily do Byzantine agreement. If n was greater than 2t, each player just sends the mediator their initial preference, and the mediator chooses the majority and tells everybody that's what you should do. What's really interesting is in the game theory literature, also in the late 80s, look at these dates and compare them to these dates back here. You see, more or less the same dates before Lewis was born, probably before most of you were born. And these are the kind of results that they had in the game theory literature. Now, I should say, Roger Myerson won a Nobel Prize. So again, my point here is the people writing these papers, Francois Forge is also a very well-known game theorist, but the people writing these papers, again, are not obscure economists. These are Nobel Prize-winning economists. This material is extremely well-known in the econ literature. So the kinds of results that they prove, and they call it implementing mediators, at a high level, they want to say, if I can do something with a mediator, can I do it without? Which, if you stand back a few yards or meters, is exactly the same problem that the computer scientists cared about. If I could do something with a mediator, like figure out the highest salary, can I do it without? For the economists, what that meant was, if you could get a Nash equilibrium with the help of a mediator, can you achieve it using cheap talk, with the players just talking to each other? Right? So what I want to say is, if you stand back a few meters, the problems that economists were looking at in the late 80s and the problem that computer scientists were looking at in the late 80s are essentially the same problem. Although they sure didn't realize this for several decades. I'm going to come back to that point. So let me start talking about the research that I was involved in. So Nash equilibrium tolerates deviations by one player. Just by definition, Nash, and I'm assuming you all know what a Nash equilibrium is. Lewis, is that fair? Can we have a quick show of hands? Is there anybody who does not know what a Nash equilibrium is?
I can't see any hands. I think we're safe.
Okay. So Nash equilibrium says that no single player can gain by deviating, but it's perfectly consistent with Nash equilibrium that two players could do better by deviating. So I'm going to say an equilibrium is K-resilient if no group of size K can gain by deviating in a coordinated way. They can talk to each other and plan out their deviation together. So let me give you an example. If we have n players, everybody plays either 0 or 1. If everybody plays 0, everybody gets 1. If exactly two players play 1, so if Lewis and I play 1, then Lewis and I get 2, and the rest of you, sorry, get 0. Otherwise, everybody gets 0. So everybody playing 0 is a Nash equilibrium. Nobody can gain by deviating. Everybody gets 1. And if anybody deviates, everybody gets 0. But it's not too resilient, because if Lewis and I get together and we both play 1, then we're going to get 2. And everybody else is getting. So if we deviate by playing 1, then we're going to get a payoff of 2. All the rest of you will get 0. Okay, so I'm hoping that's clear. So now the idea of K resilience, so you can think of Nash equilibrium as one resilience, and K resilience in general. So John Nash, in his thesis, for which he got a Turing Award, proved that Nash equilibrium always exists if you allow randomized strategies. In general, it's not that hard to show that K-resilient equilibria don't exist. That is, you can come up with a game for which there are no K-resilient, no two resilient equilibria. Interestingly, historically, over 60 years ago, Bob Bauman, who, as it happens, also won a Nobel Prize, uh, considered what he called strongly resilient equilibria, which is K-resilient for all K. And then basically you see a few papers in the game theory literature, but really hardly anything on the topic. My sociological guess is game theorists are really interested in what they call solution concepts like Nash equilibrium that make predictions about how play is going to go. And if a certain solution concept might not exist in a particular game, you can make no predictions. So they sort of tend to avoid that like the plague. So that's my guess for what it's worth as to why game theorists didn't consider K-resilient equilibria, although they strike me as extremely natural. But we want more. We want even more robustness. So let me explain. So some agents don't seem to respond to incentives, perhaps because we don't understand their utilities. So they would respond to their incentives if we understood what incentivized them, but we're just wrong. They might be irrational. They might have faulty computers, so they'd like to do the right thing, but they can't, even if they want to. And apparently irrational behavior is not that uncommon. People certainly share files and all these file sharing sites. Why are they doing this? Ties up their computer. They get no obvious benefit, but I like walking around thinking, all those movies you downloaded, they came from me. Who knows? So let me give you an example that will distinguish, that will give you a flavor of robustness. So consider a group of n bargaining agents. If they all stay in bargain, they all get a payoff of 2. Anybody who goes home gets a payoff of 1 independent of what everybody else does. But if you stay and not everybody stays, so if everybody stays, you get the 2. That's the first clause. But if you stay and some people went home, you get 0. Okay, are we together? Now, there are 2 Nash equilibria here. Again, I'd like to see a show of hands. What are the 2 Nash equilibria in this game? Louis, if you could help out here.
Yeah, sure. Do you want me to call on people? Or...
Yes, well, yeah, if somebody raises their hands. So
yeah.
Those 2 Nash equilibria, what are they?
Right, I can see some hands raised, so we just need a mic brought. I think Marta's in charge of the mic, so hopefully that's all fine.
Everyone stays is one, and everyone goes home is the other.
Exactly. Everybody stays, they all get a payoff of 2. Nobody was going to want to deviate because then if that person deviates, everybody else, they only got 1, they're worse off. Everybody going home is fine. Now, clearly everybody staying is Pareto dominant. You get a higher payoff. You get 2 instead of 1. On the other hand, if there were 10,000 people, what would you do? Would you really stay? Right? Because if you go home, you're guaranteed 1 no matter what. If you stay, you have to rely on everybody else staying before you get your 2. So this is, we're going to say, I want to distinguish resilience, which says that no group of K agents can gain by deviating, from what I'm going to call immunity, which is I'm going to allow up to T, think of them as faulty agents or agents whose utilities I don't understand. Now, I can't control what they do and I can't incentivize them because I don't understand their utilities. So the kind of robustness I want is saying those T agents, there's nothing they can do that will make me worse off. So in the case of going home, in this example, going home, everybody going home, that's a T immune equilibrium for all T, because there's nothing T guys can do. There's no deviation they can perform that would make me worse off. I get my 1 no matter what anybody else does. Whereas everybody staying and bargaining is definitely not immune. It's quite fragile. I hope that's clear. So, whoops, let me go forward. So I'm going to be interested in what we call KT robust equilibria. protocols that tolerate coalitions of size K of rational agents who can be incentivized, and up to T faulty agents, and we can't incentivize them. All we can do is argue that what they do can't hurt us. So Nash equilibrium is the special case of 1-0 robustness. K is 1, T is 0. And in general, K2 robust equilibria don't exist. But I'm tying together the threads now. There's lots of games where you can get a K2 robust equilibrium with the help of a mediator. So and the question we're going to ask is, can a K2 robust equilibrium obtained with a mediator be implemented using cheap talk? So let me explain what that means. So before going on, I want to slow down and give you a bit of technical background. So formally, there are 3 games in the picture. The first game, game number 1, is a normal form game. So this is a game where you have like a matrix that describes the payoffs. If you tell me what every player does, here's the payoff to each player. Standard normal form game in game theory. Game 2 is the game with the mediator. In that game, you can talk to the mediator can talk back. You can also talk to each other, but the interesting thing is talking to the mediator. The mediator tells you what to do, which you can ignore. It's a game, you can deviate. So what's important here is the mediator is non-strategic, in that the mediator is not going to deviate. The mediator will announce her protocol and will follow her protocol and will not deviate. The players are rational players. They might deviate, or they might be faulty, because we're looking at KT robust equilibria, that up to K players can get together and as a coalition deviate. Up to T players can perform arbitrarily, including helping the K players. And what happens in that game is, at least the way the economists model it, first we talk to the mediator. We have, a bunch of rounds of communication. And the mediator says what it says. And then we make a move in the underlying game. Remember I said there were 3 games. The first game was the normal form game. So after talking to the mediator, we make a move in the normal form game, and we get whatever payoffs we get according to the normal form game. I hope that's clear. So that was game 2. Now game 3 is what's called the communication game. There's no mediator. The players can just talk to each other. And again, after talking to each other, they make a move in the underlying game and get whatever payoffs they're going to get in the underlying game. And the question, when I say, can an equilibrium obtained with a mediator be implemented using cheap talk? In the game theory literature, so we have this equilibrium in the game with a mediator. Equilibrium means that no group of K can gain by deviating. No group of T can harm the good guys by deviating. So you've got this equilibrium, and now an equilibrium is a distribution over outcomes in the underlying game, in game 1. So the question is, can you get that equilibrium, the same distribution over outcomes as an equilibrium, in the communication game, game 3, without the mediator? So if you can get an equilibrium with the mediator, can you get the same equilibrium without the mediator? That's the question of, can you implement the mediator? Okay? That's the question I'm going to be interested in. So we have a bunch of theorems, and if I have time at the end, and I'm slightly optimistic that I will, I'll be able to give you a sense of how at least the proof of one of them goes, because I think it gives a lot of insight. Suppose you can get a KT robust equilibrium using a mediator. Then you can implement the mediator. You can get a KT robust equilibrium using cheap talk, as long as n is greater than 3 times K plus T. And you can do this even if you don't know the exact utility. It's sort of like a black box, that we run this protocol. I don't have to know your utilities. You don't have to know mine. We just run this protocol, and it runs unbounded time. By that, I mean there might be randomization along the way, but the whole protocol is done after 17 steps. Remember that, because I'm going to use facts like this to prove that results in major econ journals are wrong. Now, if you make that 2k plus 3t rather than 3k plus 3t, and assume there's a punishment strategy. Now, in a punishment strategy, it's like, okay, Lewis, if I catch you cheating, then I'm going to punish you. Punishing means there's a protocol I can run that would give you a payoff worse than you would have had you followed the recommended protocol. So I can make you worse off than you would have been otherwise. To do this, I actually need to know your utilities. So unlike part A, where the utilities don't have to be known, in part B, I may have to fine-tune the punishment. So I need to know what your utilities are, what's going to make you feel bad. And moreover, we can show that in general, this protocol, it's randomized, but among other things, you're randomizing over the stopping time. So although it has finite expected running time, there's no bound on the total running time. So, it could run 17 steps, 18 steps, 19 steps, 20 steps. Now, the probability that it runs for 20 steps is exponentially smaller than the probability it runs in 17 steps. So the expected running time is finite, but we can prove that you have to randomize over running time in general to get this to work. Hang on to that. I'm going to come back to that point. Now, if you have a broadcast channel, you can do it if 2k plus 2t is less than n, but there's a small probability your protocol won't work. If you have one-way functions, which is a major assumption in cryptography, that there are functions that you can compute in polynomial time, but you can't invert them. You can compute f, but you can't compute f inverse. And there's a punishment strategy, then you can do it if k plus t is less than n. My point here in the theorems is that we're getting these results. These are standard assumptions in the distributed computing, crypto, and econ literature. So punishment strategy comes from the econ literature. Broadcast channel absolutely comes from distributed computing literature. And one-way functions exist. There are tons of papers on this in the crypto literature. So it's sort of interesting how standard assumptions come together. So I should say that these results, the initial results, I'll be talking about recent results at the end, but these results date back to 2006. And Lewis, I see you have your hand raised, so just give me 1 second to finish this thought. But I remind you, the initial work in the econ and distributed computing community dates from the late 80s. So for almost 20 years, these two literatures, which again, not obscure papers published in the South Dakota Journal of Weird Computing, but papers written by Nobel Prize winners and Turing Award winners, these two literatures went on in parallel, blithely ignorant that the other community had been working on the same thing till we brought this together. Lewis, you had a question.
Yeah, I was just wondering if you could quickly clarify what a broadcast channel is. Is that the ability of one agent to kind of send messages to all other agents at the same time? Okay.
Exactly. So for parts A and B, we're assuming what is called a point-to-point communication. So I can send a message to you, and you know it came from me, as opposed to coming from anybody else. That's actually important. And here we're assuming, and it will arrive. In the synchronous case, which is what I'm focusing on now, and it will arrive within a round. Broadcast channels, I can send a message to the whole group, and I'm guaranteed that within a round, everybody will get it. So by all means, let me just take a quick break and ask if anybody have any questions on any of this stuff.
There was a question?
Yeah, by all means, go ahead.
Okay, yeah, sorry. My question is about the punishment strategy. So is it supposed to contrast with the exact utilities not being known? Like, for instance, is players knowing how to min-max each other sufficient?
So the punishment strategy by itself has nothing to do with the utilities not being known, but let me clarify. So typically we can choose a parameter and say we punish you this much. This is the payoff you'll get if we run the punishment strategy. Now I want to choose that payoff in such a way that if I run the punishment strategy, that payoff is significantly less. So your expected payoff if I run the punishment strategy ought to be worse than your expected payoff if you don't deviate. Does that make sense?
Yeah.
So, but to do that, it turns out I have to know which punishment strategy to run, like how to choose the parameter. And to do that, I need to know your utilities. So to use the punishment strategy, I need to know what's going to make you suffer. What will make you feel bad. And so if I don't know your utilities, having available punishment strategy turns out not to be useful because I don't know how to set the parameter. Does that make sense?
We have another question?
Sure.
Hi. So just another question clarifying the communication system. So you have the broadcast channel and the point-to-point communication.
For part C,
For part C and B.
For part A and B, there's no broadcast channel. It's just
Right.
point-to-point.
There's a point-to-point. And that's done within the single round. And I presume it's just you get to communicate to another agent or to the broadcast channel, but there's no back and forth communication, is there? In this
There can be so in any round, you can choose a subset of agents to whom you wish to communicate and send each of them a message on the point-to-point channel, which they will get by the end of the round. So I
Okay.
should stress, this is what's called the synchronous case. I'll be talking about asynchrony later in the talk. So under the assumption that the system is synchronous, the point-to-point, it's not that you can just choose one person. You can you can send messages to 5 people. They can respond after they get your message, but that's the next round.
So it's
Also,
iterated, so they
in
can
that round,
negotiate.
send you a message, but it can't be a response to your message.
Okay. That makes sense. Thank
So,
you.
Conceptually, you should think of this as there's the send phase of a round followed by the receive phase of a round. And in the receive phase of the round, you get all the messages that were sent in the sent phase, but then you can't respond to them until the send phase of the next round.
Okay. That clarifies it. Thank you.
Okay. Anything else?
No, I think we're good.
Okay, going on. It turns out that the proof of this uses what's called secret sharing and multi-party computation. And if I have time at the end, I will actually do the proof, or at least give you a sketch, because the proof, I think, gives a lot of insight, and it's cool. And more theorems. So this is a theorem that says if 3k plus 3t is greater than or equal to 10, notice it's greater than or equal to, not greater than. There is a KT robust strategy using a mediator that cannot be implemented without a mediator, without knowing the utilities. So this is saying you really need to know the utilities if 3k plus t is not greater than n. It can't be implemented without a punishment strategy. You really need a punishment strategy. And it can't be implemented in bounded time. So you can do it in bounded expected time, but it might take an unbounded amount of time. Other similar, so these are lower bounds. I should stress there's an exists here. These results are saying for all games, if these bounds hold, you can implement the mediator. The lower bounds are saying there exists a game for which the bounds of the previous theorem don't hold, and you can't implement the mediator. They are not saying that for every game, it could be that you can implement the mediator even if n is a lot less than 3k plus t in some simple games, right? So these are existential results. There exists a game where you can't implement the mediator. And so there's more results in that flavor. I don't want to go into all the great details. And the techniques we use here, some of them were borrowed from the Byzantine agreement literature in distributed computing. Some of them, I think, are new. But basically, they're matching lower bounds with the understanding of the quantification. Here it's saying for all games, if these bounds are met, you can implement the mediator. And the lower bounds are saying there exists a game, if these bounds aren't met, there exists a game where these bounds aren't met where you can't implement the mediator. And this one is saying that you need to randomize. Randomization is good. So why am I doing all of this? Well, so first I want to relate this to what was done in CS and game theory. So as I said, Forge and another Hungarian mathematician, Barney, proved theorem 1A. That's this one. Now, they were interested in Nash equilibrium. So they were interested in the case that K is 1 and T is 0. And they said you can implement the mediator as long as there's at least 4 players. Right? That would be the special case where K is 1 and T is 0. So we're greatly extending the result to allow coalitions and to allow faulty players. But nevertheless, what's cool is that they use pretty elementary techniques. For us to extend the result to all K and T, at least our proof, we needed to use in a serious way work from cryptography on multi-party computation. So this is, again, tying the threads together, bringing ideas. So one message I give when I talk to game theorists is, you guys ought to learn some stuff on cryptography or multi-party computation. It really comes in handy for some of these results that you want to prove. Now, Ben Porat, Elchanan Ben Porat is an Israeli game theorist. He was the one who introduced the idea of punishment strategies. So again, he proved theorem 1B in the special case of Nash equilibrium, or at least he published a paper in a leading journal with the claim to a proof. So K is 1 and T is 0. So he said if N is greater than 3 and there's a punishment strategy, then you can implement the mediator. This is true. Unfortunately, his proof is buggy in a serious way, which I'll explain. Yuval Harari, another Israeli economist, extended the ideas of Ben Porat to all K. He was also interested in coalitions. Now, Ben Porat's strategy, when we looked at it, which was published in the journal JET, which is Journal of Economic Theory, which is a major econ journal, we knew it had to be wrong. Why did we know it had to be wrong? Because if you look at a strategy, even if you don't read anything about the details, you can see this is a strategy that runs, actually, I think it's something like 7 steps. Step 1, step 2, step 3, 4, 5, 6, 7. Done. So it's a bounded strategy. It takes 7 steps. We have a theorem that says there's no way you can do this with a bounded strategy. You have to randomize. That was this one, that you can't do it in bounded time. So, oops. So after figuring out that it had to be wrong, it took us a while to figure out where the bug was. But we knew there had to be a bug. We knew that even before we found it, because we knew that there is no way there's a bounded strategy. So Elchanan has a fix that uses a notion. He agrees that his paper is buggy, and he adds an extra assumption called verifiability that fixes the problem, but it's unimplementable, and doesn't really deal with the basic problem. Lisanskaya and Triandopoulos proved theorem 1C for K equals 1. These are computer scientists. But Tal Rabin and Mickey Ben-Or essentially gave theorem 1C for all K and T, again, using cryptographic techniques. Now it gets even more interesting. Urbana and Villa, again, economists, published a paper in Econometrica, which is arguably the leading journal in economics, that got theorem 1D in the case K equals 1 and N equals 2. Well, again, they had a bounded strategy. You don't have to read the details of their rather ugly strategy carefully to see that it runs in, I forget how many rounds, maybe 7 or something like that, but bounded. So we knew walking in the door, it has to be buggy. And again, after a few days of extra work, we figured out where the bug lay, and they agreed there was a bug, so there's no science is going along as it should. But these results that say that you can't do it deterministically and there's no bounded algorithm, they have a lot of bite, especially when you read papers that give you bounded algorithms that have to be wrong up front. Okay, let me get to more recent work. More recent means the last couple of years. So what's really, to a computer scientist, weird, I think I can say that, is that the econ results all assume the systems are synchronous. That by itself isn't weird. But they go and say, okay, we have a certain number of rounds. Then somehow magically a bell rings and we know we're supposed to stop communicating. And in the next round, we all make a move in the underlying game and get our payoff. Now, all the algorithms work like that. They communicate with each other, then make a move in the same round. But there's a lot of focus. If any of you have taken courses in distributed computing, you'll know that there's a lot of work in asynchronous systems. Bitcoin is what's called a semi-synchronous system, where there's a bound, in general, in asynchronous systems, there's no bound in message delivery time. I send you a message, it might never arrive, it might arrive in 17 rounds and 23 rounds. Certainly there's no promise it'll arrive in the next round. And implicitly, we assume that there's a scheduler who decides who moves when. So the fact that, you're all set to send me a message, okay, the scheduler decides when you get to go and send me a message. So there's a scheduler that really decides two things. When agents move, typically with a constraint that it won't block them from moving forever, but there's no bound in how long it might take for an agent to get around to being scheduled. And once you're scheduled, if you send messages, the scheduler decides how long each of the messages you send, how long it's going to take to arrive. And one possible answer is never. And in this setting, the cheap talk phase, it doesn't end simultaneously for all players. Simultaneously doesn't even have a good meaning in an asynchronous setting. Distributed computing people are really interested in asynchronous algorithms. This is an empirical statement. Markets are asynchronous. I mean, there's, nobody ringing a bell that says, okay, trade. Well, actually, there is somebody ringing a bell saying trading is over sometimes, but in general, things proceed asynchronously. Blockchain assumes what's called partial synchrony, where there is a bound on how long it takes messages to arrive, not one, so they might not arrive in the next round. They'll take up to 22 rounds to arrive. And the scheduler has some flexibility, but not complete flexibility. So asynchrony is really, distributed computing people really like to be able to show that algorithms will work in the asynchronous setting. So now we want to talk about implementation in the asynchronous setting. First question is, what does it even mean? The problem is that the outcome of a game might depend on the scheduler. So you might get different outcomes depending on what order players are scheduled in. If I go before Lewis, we might get a different outcome than if Lewis goes before me. And for sure, it might depend on how long messages take to arrive. So formally, when we say we're implementing a mediator, we want it to be the case that for each scheduler in the mediator game, there's a corresponding scheduler in the communication game that implements the same outcome. Because remember, for different schedulers, you're going to get different outcomes. So there can't be one scheduler that implements all outcomes. No hope. And the interesting thing is that what we get is numbers go up by 1. So this is, 4a is an analog to 3a that says rather than you can do it if n is greater than 3 times k plus t, you can do it if n is greater than 4 k plus t. I should say this is joint work with my student Ivan Gefna. And we had, there was a 3b that talked about 2k plus 3t, and now bumps up to 3k plus 4t. And the intuition is that dealing with asynchrony, what you have to worry about is that you can't tell the difference between, if I don't get a message from you, is it because you're faulty and you're deliberately not sending me a message? Or is it because the scheduler has delayed your message and if I just wait a little bit longer, I'll get it? And it turns out that dealing with that basically costs you, you need extra players to make sure that things work. So let me stop, but I'm going to have time to do the proof. And allow for questions. So I give this talk to both economists. I gave this talk at the University of Chicago, which has all these Nobel Prize winning economists, with Roger Myerson in the audience, which is great. Roger's a great guy and asks lots of smart questions. And I give this talk to computer scientists, and of course I want to focus on different things. So that issues of coalitions and fault tolerance, which are standard in distributed computing and cryptography, I think that game theory needs to take them more seriously. And asynchrony is another issue that, I mean, I'm now making an empirical statement. I would guess that 98% of papers in the game theory literature focus on the synchronous case, whereas in the distributed computing literature, certainly the majority focus on the asynchronous case. That's a cultural phenomenon. I mean, that's the way it's been historically. But I think game theory needs to take asynchrony far more seriously, because in the real world, there's lots of asynchrony. Now, one thing I haven't looked at here, but something I'm personally very interested in, is I haven't taken computational issues into account. You know, if you have resource-bounded players, how does that affect things? I have things to say about it, but that's a whole other talk. So I don't think Louis would be too happy if I took another hour. Okay, so that's the big picture. Let me stop for a couple of minutes. I want about 5 minutes at the end to give you the big picture of the proof. But if people have questions, I'm happy to answer questions. So this normally would be the end of the talk, except I want to tell you how the proof works.
Okay, great. Thank you, Joe. So I think it might be easier if people, Marta doesn't have to be kind of rushing around with the mic. If people want to submit their questions on Slido as normal, I can read them out. I've got a few here already.
Okay.
So maybe I can just start with those. And then I'll give people a chance to add other questions, upvotes, questions that are already there. But one of the first ones, and maybe this is actually, you might want to defer this one if the proof is going to go into this anyway,
Right.
but is there a general pattern for how the mediator is implemented? Is there a kind of key intuition and trick behind this?
Yes, and I'll defer that till I explain how the proof works. That's exactly what I'll be talking about.
Okay, perfect. So that we can rule that one out. That's done. Second one I have here is you've been a proponent of solution concepts for the 21st century.
Yes.
How do we think about equilibria in worlds with advanced AI systems, e.g. things like language model agents and other sorts of things like that? How do the notions of equilibria apply when we have these kind of slightly fuzzier agents without explicitly
That's
representing?
a great question. I really haven't thought about that, but the question is, do you want to view an LLM as an agent? And if so, I mean, equilibria, by and large, don't make sense unless you have agents with utilities. So do you want to think of the LLM as having utility? In some sense, I think the answer is yes. I mean, why is the, LLM making stuff up? It's trying to please you. And maybe it has some utility at giving answers that please the questioner. So I think it would be really interesting to think of, so I haven't thought about it. I would be happy to talk more about it, but I don't have any deep insights here. But I think it would be really interesting and an interesting way to approach LLMs. If we think of them as agents, what is their utility function? And once we have a utility function, then indeed, I think we can think about equilibria and so on.
Nice, thanks. I have one more here at the moment, which is what other ideas and insights from economics or cryptography do you think the fields of computer science, AI, game theory, whatever they might be, would benefit from importing or considering more deeply? And I guess this question is, the person writes, especially for cooperation. So I suppose that's the kind of topic of.
Yeah, so I
today.
didn't say a lot about cooperation here, but I hope it was at least implicitly clear that one way of getting cooperation would be to implement a mediator. One thing I'm really interested in, but you're getting my bias, is that I would like to see solution concepts that take into account a variety of player types. So basically, economists have focused on rational players who gain by deviating. Here we introduced also faulty players whose utilities you don't understand. But I can imagine altruistic players who, who sort of, look, I'm willing to go along and do what I'm supposed to do as long as other people are doing it and I don't feel like a jerk. Let me make, I'm sort of, we get some societies, and I'll take North America as an example of this, where by and large people pay taxes because they expect other people to pay taxes. Now, it's not perfect. I know people cheat, and I know some people cheat a lot, but most people pay taxes. By way of contrast, in a place like Greece, hardly anybody pays taxes. And you feel like a fool if you're paying taxes because nobody else is paying taxes. So I'd like to see notions of cooperative equilibrium that take into account that some fraction of players aren't going to be rational, aren't going to be faulty, but are going to cooperate. But they're conditional cooperators, that they won't cooperate if they get the news that nobody else is cooperating. So it's more or less, I'll cooperate if you will, even if I could gain by deviating. So I want to distinguish this from rational players. So that's an idea that I personally would like to explore. It would lead to a more general notion of equilibrium. And I think it reflects the real world, that there are people who are willing to cooperate, even if it's not necessarily, I think of myself as a nice guy. So psychologically, that I'll cooperate, but boy, if I feel like nobody else is cooperating, I don't want to be a jerk. I'm not going to cooperate. So that's one example. I'm not sure if you count that as a CS idea, an econ idea, but it's an idea that I think originated in CS literature, but certainly doesn't have a. I think notions like blockchain are introducing lots of economists to issues of asynchrony and partial information that didn't come up in standard games. So it's another influence of computer science. Louis, I say I have 5 minutes to go. Do you think it would be reasonable for me to spend these last 5 minutes now doing the proof? Or talking?
Yeah, I think that's great. It'd be good to get, I think, an intuition for that. I'm personally
Right.
interested, at least.
So,
Thanks.
So the idea of the proof goes back to Adi Shamil, another Turing Award winner, Israeli computer scientist. He wrote a paper, a lovely, lovely short paper on secret sharing. So how many people are familiar with this? Maybe a show of hands, because I'll explain it.
I cannot see any hands from
Okay, so here's the idea. Suppose I have a secret that I want to share in such a way that no group of size M can figure out the secret, but any group of size M+1 can get together and figure out the secret. So I'm going to give each agent some information, and I'm going to do it in such a way that no group of size M, even if they pool their information, has any clue of what the secret is, but a group of size M+1 can figure it out. So here's the idea that's beautiful. Take a polynomial of degree M. Take the secret to be f of 0. Now I'm going to give agent 1 f of 1, agent 2 f of 2, agent 3 f of 3. So each agent gets a point on the polynomial. Now it's perhaps easiest to think about this if we talk about if m is 1 and we have the polynomial happens to be a line. So we got a line. Where it crosses the y-axis, that's the secret. I'm going to give f of 1 to Louis, f of 2 to somebody else. Now, if Louis and whoever else, and Marta, get together, they'll have 2 points in the line. With 2 points, you can reconstruct the line, and therefore figure out f of 0. Done. You know the secret. But Louis by himself, Marta by herself, no agent by himself, they'll have 1 point in the line. There's infinitely many lines that go through this 1 point. You have no clue what the secret is. That generalizes, it's not very hard to prove using some algebra, that if you have a polynomial of degree m, like take a parabola, has degree 2, 3 points determine the parabola. There's a unique parabola going through 3 points. 2 points, infinitely many parabolas. And in general, if you have a polynomial of degree m plus 1 points completely determine that polynomial. So if m plus 1 people get together, share their m plus 1 points, they can figure out the polynomial. And therefore, they can figure out the secret. No group of m can figure out the secret. So this is a really short paper, by the way, if you want to read the original. But I really summarized it, and the algebra is high school algebra. So it's just a beautiful insight, which I wish I could claim credit for, but it's additional. So that's the key notion. The other part of implementing the mediator is we want to be able to view the mediator as performing a circuit computation. What I mean by that is at the top, there's the inputs. Think of each agent has an input. So when I have x1 to xn, it's because there are n agents. Each one of them has their input. And I'm going to assume that what the mediator does in that second game, the game with the mediator's protocol can be described by a circuit. A circuit is a very general model, so this is not an unreasonable assumption. But I'm going to assume that all the gates in the circuit, all these computations here, are either addition gates or multiplication gates. And again, you'll have to take my word for it. This is a pretty general model. You can capture lots of mediator protocols this way. And what Benoit Goldwasser, there should be Vigderson, not Sigderson. Again, just won the Turing Award, so did Chaffee. They gave, I think it's Goldreich, not Goldwasser. I think there might be a bug there. What they showed is you could simulate this circuit in such a way that each agent, we're going to use ideas of secret sharing, this previous slide. I mean, they're deeply connected. So what's going to happen at step 1, agent 1, whose input is x1, will give each of the agents a share of x1. When I say a share, I mean literally agent 1 will come up with a polynomial of degree, if you want to tolerate m faulty agents, of degree m, well, if you want to tolerate m plus 1 agents, so that no group of m can get together and figure out agent 1's input, but any group of m plus 1 could get together and figure it out. So agent 1 will share his input, agent 2 will share her input, agent 3 will share her input. And share just means pick a polynomial at random and give each agent a different point on the polynomial. And at each step in the circuit, if this step was the result of adding together these two inputs, what Benoit Goldwasser and Vigderson showed is there's a way to, again, ensure that if each of the agents had a share in the inputs of the computation, they'll have a share in the output of the computation. If the step is just addition, it turns out the share is just sum my shares of the two inputs. That'll be my share of the output. If it's a multiplication gate, it's much more complicated, but it's been done. So basically what's happening at each step in the circuit, the agents do the computation, they go step by step, layer by layer, and they'll always have a share of whatever the value is of the node at that step. Like they would have a share of the value of this node right here. So once they've gone through the whole circuit at the very end, they'll all have a share of the output. But they won't have any clue what the output is. They'll just have a share unless m plus 1 of them get together. So at the very end, they all send each other their shares so they can figure out the output. So they can basically reconstruct the mediator's protocol in this way, keeping all along the way the protocol secret. They have no clue what it is up until the end when there's the big reveal, so to speak. So that's the idea of the proof. Now let me give you some insight into where that 3 came from in the 3k plus t. So think of a line. Now, if I have one faulty agent, the agent, no, how do I say this? If I have, let me take the case where K is 1. So if I have 3 agents, and one of them is faulty, and that one agent lies about their input, and I know the secret is f of 0 where f is a line, degree 1. So what I'll have is 3 points in the line. And if one of them lied about the input, the 3 points won't be collinear. Right? I'll have a point here, and a point here. The trouble is, I won't know which of the 2 guys is telling the truth, so I won't know which is the right line. But now suppose I had 4 guys, 3 times 1 plus 1. Now if one guy lies, the other 3 are telling the truth. There will be 3 points that lie on the same line. So not only will I be able to figure out the line, I'll be able to figure out who's lying. This generalizes. In general, if I have 3k plus 1 agents and a polynomial of degree k, if k people lie and I have 3k plus 1 agents, I can figure out the k liars and figure out the polynomial. K liars won't stop me from figuring out the polynomial. K plus 1 liars will. So that's sort of where the 3k plus 1, at least in this proof, is coming from. It gives you enough points on the polynomial so that k guys can't stop you from figuring. Again, the line is the easiest thing to think about. If k is 1, then 3k plus 1 is 4. If you have 4 points, even if you have a liar, you know who the liar is because the points are all supposed to be in the same line, and there will be 3 collinear points. Those have to be the points on the line. And the guy who's not collinear, he's lying. But if you only have 3 guys, you can't do this. So I thought that was cool. Again, I can't take any credit for this, but that's the way it is. Okay, so I hope that gives you some idea of the proof. And let me stop there. Let me say I will have office hours. I'm in my room. I'm going to go outside to the patio, and I'll be wearing a mask. I believe at this point I'm not contagious, but I could be wrong. So, it's sort of at your own risk, so to speak. We can separate as far as you'd like. Give me 5 minutes to get there. But I'll be sitting there for the next hour to hold office hours. But if you're willing, Louis, I'm happy to answer more questions on this last part as well.
Just kind of ask the audience and everyone in the room to give one final round of applause for Joe. For